Okay, chapter 3 is all about exponential functions and logarithms. Logarithms aren't bad. Okay, one of the biggest mistakes students make when solving exponential equations and logarithm equations. Students you will learn your log rules. I know it. You'll be good at them. The problem is you will start using log rules that aren't real. Okay? People are constantly doing things that there is no rule for. And one of the hardest things in math isn't just knowing stuff and knowing what you know, it's knowing what you don't know. You don't have a rule for it. Or in fact, knowing that this thing I just did actually is not correct. How often do you see people like, oh, the square root of x squared plus 9, that's just x plus 3. Right? What rules, why using rules is this wrong?
Plus or minus?
Right? Well, think about it. If that was true, then what would the square root of 16 plus 9 be? If that was true, wouldn't this be 4 plus 3, which is 7? But what is the square root of 25? Yeah, and last I checked, 7 and 5, not the same number. Okay? So stuff like that. Knowing that we don't have a rule that lets me do this because it's so tempting. And what's that?
How would you solve that?
Boom, done. That's as simplified as that gets. You can't, you can't do anything to that. Okay? Yeah, the square root of x squared plus 9 does not in any way, shape, or form simplify. You cannot distribute radicals over addition or subtraction. Okay? So making sure you're aware of these rules, these things you're not allowed to do are important. This happens a lot with logarithms. I'll see people like 2 to the x equals 5 minus 2 to the negative x. And they'll all be like, oh man, log that, until they end up with something like that, which I wish it was that easy. In fact, that ends up being no solution, which is not the case at all. There is not a rule that lets you just logarithm the individual terms. Okay, we don't have a rule that lets you break a logarithm up over addition and subtraction. So make sure you are aware not only of what the log rules are, but what aren't log rules. Okay? So that way you're not mistakenly doing things that are not allowed. Today we're just going to focus on exponentials. We will review logarithms pretty much from the ground up because a lot of you are probably like, what is a logarithm? Okay? In fact, the reality is, how many of you have what you feel is at least a decent basic understanding of exponential functions? Okay, that's good. Should be most of you. Hey, what's up? There you go, sir. Enjoy. You got a cheap calculator? No, I got it. Yep. Okay. So, a lot of you raise your hand as having a decent understanding of exponential functions. How many of you feel like you have a decent understanding of inverse functions? Right? We already did it in chapter 1. So, with those two things combined, if you know exponential functions real well and you know inverse functions real well, you already know logarithms. There's not really anything new to learn. Conceptually, you've got it all. Because all logarithms are is inverses of exponentials. That's it. That's all they are. What's an exponential? Great question. What's an exponential function? Grows exponentially. What does that mean? So I saw Dalton doing this with his hand there. Graphs that look like that. From left to right, they are constantly increasing, always going up.
Or they could always be going down.
Or they could be always going down, or, yeah, lots of different ways if you flip them and reflect them and stuff. But that's what a basic exponential looks like. Okay, very different than a parabola. A parabola is not always increasing. It's half decreasing, half increasing. What does the equation of an exponential like this look like? Y equals What's that? Pick something. Pick a 3. All right. A. Okay, so maybe this is 3 to the x. The big difference between a power function and an exponential function is that an exponential function, your base is a constant, your exponent is the variable. Whereas in a power function like 3 to the x, or nope, x to the third, there we go, your base is the variable and your exponent is constant. Okay? So that's a basic exponential function. What are some real-life examples of exponential functions? Logistic growth, like bacteria growth, right? Lots of populations grow exponentially. Bacteria especially, because how do bacteria reproduce? They split in half, right? That binary fission idea, correct? And so bacteria growth would actually be more closely related to the function 2 to the x, where maybe at time 0, what's 2 to the 0th power? You have 1 bacteria, and then after 1 reproduction cycle, plug 1 in, you have 2. Then plug 3 in, what's 2 to the 3rd? Or sorry, plug 2 in, what's 2 to the 2nd? And what's 2 to the 3rd? And so you get this exponential 32, 64, 128, 256, 512, 1024, 2048, 4096, and eventually your bacteria population gets so gigantic it covers everything on the earth, which doesn't actually happen because eventually the population reaches what's called the carrying capacity of their environment, and so they start dying off as fast as they're reproducing. So you get exponential growth at first, and then it's a piecewise function actually. It's exponential at first, and then it levels off to the carrying capacity. Where else do you see numbers like this?
Technology.
Numbers that follow an exponential pattern. Technology, right? Because everything on a computer is 1s and 0s. So there's 2 options for everything. So if I take 8 bits of data, done? Oh, you have questions? Oh, yeah. Just state all of them, but for the vertical asymptotes and holes, rate limits. Just for the vertical asymptotes and holes. So 8 bits of data. How many options are there for this bit? It's either 1 or a 0, so there's 2 options. There's 2 options for this, and there's 2 options for this, and there's 2 options for this. So eventually, you get 2 times itself 8 different times. So how many different things can you encode using 8 1s and 0s? Whatever 2 to the 8th is. 256. So there's 256 different things that a single byte of data on a computer can represent. A byte is 8 bits, 8 1s and 0s. Guess how many kilobytes guess how many bytes are in 1 kilobyte? 1024. Or more specifically, that would be exactly how many different numbers you can encode in a kilobyte. And so on. So you've seen these numbers a lot. Like you never see a computer that has 300 megabytes of memory, and either 256 or 512 or a gigabyte or 2 gigabytes. Everything's always in these multiples of 2. It's deceiving because they don't sell a hard drive with literally how many ones. They don't tell you how many bits it can store. They tell you how many different numbers you can encode because that seems like a higher number. Where else do you see exponential functions?
Well, if you have a body that is falling, its speed will increase with its velocity.
Right. But its speed will increase linearly. Its position will increase not exponentially, but quadratically of power. So those are power functions, not exponential. Interest. Either if you invest money, how your money grows, or if you're borrowing money and figuring out how much money you owe the bank. That is all exponential growth. It's funny because have you ever heard somebody describe something as growing exponentially?
Yeah.
They're usually describing something that's growing how? Very, very quickly, right? So we often say if something grows really high, really huge, really fast, we say it grew exponentially. But yet, money in a savings account technically is growing exponentially. And is it growing really huge, really fast? No, I mean, I guess it's a relative statement. You know, if we take a billion years, then yes, money in the savings account does grow really big, really fast within that billion years. Everything's relative. To us, no. Money does not grow really big, really fast in a savings account. Now, how is money exponential growth? Let's say I start off with $1,000. And let's say I put it in a savings account that makes 3% annual interest. What's that? Say once a year. Okay, so once a year our money grows by 3%, which is not actually how banks work, but we'll pretend that it is. Then, how much money do I have at the end of 1 year? So how would you calculate that? How do you calculate an increase by 3%? So you want to do 0.03 of how much money I have, which is 1,000, and then add that to 1,000. That's great. Now, if we look at this, can't we factor that 1,000 out?
Yeah.
And so I end up with 0.03 plus 1. So essentially, can't I just take 1,000 and multiply it by a 1.03? Won't that do the same thing? Does that make sense? So we can let's start with $1,000, and let's multiply it by 1.03. And so at the end of 1 year, I've made $30. How about that? Now, how much money will I make the second year? Just barely more than 30, because not only will I get 3% of my original $1,000 investment, I'm also going to get a 3% increase of the $30 I made over the previous year, and that is what makes it exponential. I made an extra 90 cents in that second year than I did in the first year. Right, because doesn't this? So after I start with $1,000, then I have 1,030, then I have $1,060.90. Then I have $1,092.72. You better believe the bank's not rounding that up to 73, right? Am I right? I don't know. Maybe banks round. I'm not sure. But how are we calculating these numbers? Well, this right here is 1,000 times 1.03. This number here was 1,000 times 1.03 times another 1.03. This number right here is 1,000 times 1.03 to the third. So what exponential function can I make that represents how much money I have in my bank account? 1,000 times 1.03 to the x. And if I just plug in a year for x, so for example, in this savings account that makes me around $30 a year at least to start, how much money will I have if I can just let that money sit in that savings account for how many years? 20 years. I will have made $800 at the end of 20 years. Nice. Okay, what if I eventually become immortal and I just let that savings account go for 500 years? How much money will I have? Yeah! Woo! $2 billion! Yes! Of which in 500 years that'll probably be worth what, like $1,000 is worth now, but I don't know. What is interest rate? Or inflation, yeah. 0.04? Oh, that'll be worth a lot. That'll be worth well more than 1,000. If I make it 3% a year, that's 0.04%. Yeah. Unless we experience hyperinflation like Zimbabwe. Has anybody ever heard about Zimbabwe?
Oh, I remember. I don't know.
Zimbabwe.
I know it is.
Zimbabwe is actually, you've heard the name Zimbabwe. Good, that's good. It's in Europe. No, in Africa. Okay. Just testing you. All right. Very confident with your Zimbabwe knowledge. No, Zimbabwe actually experiences self-induced hyperinflation. I don't know what that means. For some reason, they force this crazy high inflation because essentially it works like, basically the government can say, hey, we want you to build a new building for us. We will pay you $300,000. And the company says, okay, great. So they start building this building. Well, by the time the construction is done, and the government pays them $300,000, $300,000 is no longer worth hardly anything. And so they've created this crazy inflation basically so that they can...
Doesn't that wreck their economy?
Oh, I'm sure it does.
Then why do it?
Why do it? I don't know. But you can go on eBay right now and buy a $1 trillion bill, a legitimate $1 trillion bill from Zimbabwe. You can get it for like $20. It says like $1 trillion. Yeah, so it's pretty crazy. You can actually do it. So like a lot of people, you may have gotten an email. There's this spam email that goes around saying, send $200. There's this money waiting on you. There's this lost Zimbabwe treasure. If you send in $200, we can give you a portion of this treasure, which is worth $2 million. Well, 2 million Zimbabwe is like $10. So people are like, this is a scam. The reality is, it's probably not a scam. I bet you if you send in $200, they probably send you a $1 million bill. The thing is, 1 million Zimbabwe is not worth anything. And so a lot of people, I can't imagine that tricks people, but you never know. Most likely, most people see that and they're like, yeah, that's a lie. It might not be a lie. Okay. Now, is this how bank savings accounts really work? Do they really once a year just increase how much you have by 3%? If that was the case, if January 1st was when they increased your bank account every year, I would leave my bank account empty all year. Then December 31st, I'd borrow money from all my friends. I'd get like $10,000 in there just for a couple minutes. Just right before midnight. Just like, hey, let me borrow $1,000. I'll give it back to you in 2 minutes. And then like 11:59 on December 31st, I put like $100,000 in my savings account, increases 3%, take that money back out, and give it all my friends. Maybe leave the profit in there. No, that's not how banks work. Does anybody know how banks actually give you a 3% annual interest rate without actually doing 3% once a year?
Is it compounding continuously using E?
Right. Well, I don't know what that means, but they compound the investment. So what does compounding mean? Let's suppose they take this investment and they compound it, let's say monthly, which is also not what they do. But that's how when you buy a house, you borrow money from the bank. Let's say you borrow $100,000 from the bank to buy a house. They say, okay, here's $100,000, but we're going to charge you, let's say right now, 3% interest. Interest rates are really low. Then they will actually increase how much money you owe them by 3% once a month. So once a month, they take what you owe them and they increase it. But they don't actually increase it 3%. Okay? 3% is what it will be on average for the whole year. What they do is they take 3% and they divide that by 12. Okay, so what is 0.03 divided by 12? 0.0025. What they actually do is they increase how much you owe them by 0.25% each month. But they do it 12 times. So if you think about it, that percentage 12 times for the year is then essentially going to be like 3%. Right? So that's the idea. So let's say we have a bank account that doesn't increase my money by 3% one time a year. They increase my money by 0.25%. A tiny, tiny amount. But they do it for me 12 different times throughout the year. Okay? So, if we take $1,000, and then I multiply that by 1.0025, At the end of 1 month, I have made $2.50. All right. All right. After the second month, I now have $1,005 and 0.6 cents. Okay? At the end of the third month, 4th, 5th, 6th, 7, 8, 9, 10, 11, 12. At the end of 1 year, I have made $1,030.41. Okay? Oh, they're not going to round that up. It's a bank. All right. Anybody ever seen Office Space? So the guys, they get fed up with their work. So they decide they're going to create this scam where they write some code that takes every single money transaction the company does and rounds that decimal part off. Because usually they just round it down. Well, they actually take that fraction of a penny and put it in a side bank account, and they just hope that after maybe 5 years, it's accumulated maybe a couple $100,000. Well, when he writes his code, the hacker, he misplaces a decimal point, so they've made like over millions of dollars within a week. And they're all freaking out because they're stealing money from the company. Funny movie. Anyway, when this same investment, the same interest rate, 3% annual interest, when it was only compounded one time for the year, how much money did it make us? $30. We had 1,030. Compounding it monthly actually made us more money. Why? Because there's that first month where I made $250. I'm now growing that money as well. Okay? And so it all builds up, and I ended up with an extra 42 cents. How many times do banks actually compound your investment in the year? Oh, more often than that. Infinitely many times. It's called compounding continuously. So, what this means is, if I were to take this 3% and divide it by infinity, but then raise that to the infinity power, and multiply that by my $1,000 investment, that would essentially be how much money I get. Okay? So, and then somehow that ends up bringing in the number E. Crazy. How is that E? But we'll get there. So investments, and we'll go over investment problems in a little bit more detail when we get to it. But for now, I felt it would be more fun to talk about investments than actually graph exponentials. They're pretty easy to graph. So you'll have homework graphing some exponentials, graphing, talking about stretching and shifting and reflecting. You'll introduce this base E, some graphs, pretty easy homework. We'll go over a couple of them tomorrow just to make sure you know how to graph them.